Alright, welcome back to our discussion about applications of trig functions. And in this video, we're going to talk about simple harmonic motion and how we can model that using the sine or cosine function. So let's talk about that. So simple harmonic motion, that sounds awfully complicated, but it's really not. Okay, what that is just an up and down motion. It's an oscillation. And if we just have that motion that goes up and down, and we disregard friction or air resistance, that is called simple harmonic motion. Okay, so let's talk about that a little bit. If we think about this ball on a spring here, this is a very elementary example of simple harmonic motion. We've got a ball on a string, and we pull it down, and when we release it, it's going to bounce, but it's not going to bounce all the way to the top of the spring, right? It's going to bounce a certain amount up and then a certain amount down, and a certain amount, and eventually it will stop bouncing. That level where it stops bouncing is called equilibrium, okay? So the rest position of an object is called the equilibrium. We find that at the midline of a graph. Okay, so as you may have noticed, this is going to be going up and down and up and down and up and down, kind of like a sine or a cosine graph, right? And so the equilibrium position of an object is at the midline on the graph. Okay, so we use a d-axis to describe the distance from the rest position after t seconds. Okay, so that is going to be the distance from the rest position. Okay, and so if we put a vertical line here, we would call that our d-axis. Right? Simple harmonic motion uses one of these two equations. D is equal to a times the sine of omega t, or d equals a times the cosine of omega t. Depending on what we're doing, we'll use either sine or cosine. This looks an awful lot like a simple sinusoidal function, right? Okay, instead of using x for our variable, we're using t because this is going to be a function of time. All right, so the maximum displacement, the maximum amount this object can go from its equilibrium, right, is going to be the amplitude of our function, right? So we can find that maximum displacement there. The period of the motion is the length of time it takes to complete one full cycle, just like a sinusoidal function. So if you pull that ball down and release it, how long does it take to go up to the top and back to the bottom? And we use 2 pi over omega, which is the coefficient to t, to represent our period. All right, and then we also will talk about the frequency of an object, and that is found by the reciprocal of the period, also known as omega over 2 pi. Okay, so let's look at what does this look like if we were to visualize that ball going up and down, right? So here is a little animation that kind of shows how this models a sinusoidal function. And of course, it would keep going, but this graph is limited, so it doesn't go off the screen, but that is the idea of this motion. All right, so let's look at an example. Okay, we have a ball on a spring, all right, and the ball is pulled 6 inches below the rest position, and then it's released. It takes 4 seconds for the ball to return to its starting position once it's released. Write the equation for the ball's simple harmonic motion. Okay, so the first thing I want you to think about is, would this be a sine function or a cosine function? We're taking the ball, we're bringing it down to the minimum point and then releasing it. So it's starting at a minimum. And if you remember what the graphs of sine and cosine are, remember sine begins at the midpoint or the midline of the function, whereas cosine will start at a max or min. So we're going to call that a cosine function. All right, so then what is going to be the maximum displacement? How far was that ball pulled from its equilibrium? And we can say that that's going to be 6 inches. How about the period? Remember, the period is how long does it take to go through one complete cycle? And that will be 4 seconds. And we remember that we defined our period to be 2 pi divided by omega. So we can say 2 pi over omega is 4 seconds, and that will allow us to solve for omega. And omega will end up being pi over 2 here. All right, and then the last thing, we're just going to put all the pieces together. We already said it's going to be a cosine function, so we're going to use this model, d equals a times the cosine of omega t. And so we can fill in a and fill in omega. Now, notice it's a cosine function, but we're starting at the minimum, and so we're going to say that d is equal to negative 6 cosine of pi over 2 times t. Right, that's pretty good. Not too bad, right? Next problem we're looking at will be an object moving in simple harmonic motion is described by this function. D is equal to 12 times the cosine of pi over 4t, where t is measured in seconds and d is measured in centimeters. Okay, we are going to find these 3 things. What's the maximum displacement? What's the frequency? And what's the time required for one cycle? So this is kind of going backwards from what we just did, right? We're given the function, and then we want to identify these key elements of this object and its motion. Okay, so how do we find the maximum displacement? Do you remember how to do that? That's really the amplitude of the function. And so we can say that that's going to be the absolute value of 12 or 12 centimeters. And in this kind of case, we need to make sure that we are identifying our units of measure. Okay, so now the frequency. The frequency, remember, is the reciprocal of the period. So the period is 2 pi over omega. So from the frequency is going to be omega over 2 pi. Okay, and so omega here is pi over 4. So we can sub that in. And then we can simplify this entire expression, pi over 4 divided by 2 pi. And that's going to give us 1/8. And then we want to say, well, 1/8 what, right? The frequency is telling us how many cycles does this object move through per unit of time. And we are measuring our time in seconds. So this is going to go through 1/8 of a cycle per second. Now our period is just going to be the reciprocal of this. And you can start back here if you'd like, but you could actually take the reciprocal of this value as well. We can just say that this is 8 seconds per cycle. And really this relationship makes sense because it's really 1 cycle per 8 seconds. And so depending on how you write it, it's either one cycle over 8 seconds, which is 1/8 of a cycle per second, or 8 seconds per 1 cycle. And it's the same relationship. That wraps up simple harmonic motion and applications of trig functions. I'll see you next time.